In this video, we're going to begin talking about surfaces and area. And what we're going to do is we're going to find parameterizations and we're going to use them to express the area of a surface as a double integral. Formerly, we had parametrized some vector r in terms of t. And now we're going to have that vector r in terms of two variables, u and v. So let's define our new vector r and try to think about how our region will relate to our surface in this context. So the idea here is we have this r being a function of u and v, not just a single variable t. Now, why are we using u and v and not x and y? Simply because it's confusing, because most of the time our functions normally have an x and a y in them. So it's just kind of a new way of thinking about these parametric components being multivariable functions. So considering this region R, and we have this R continuous vector function in the region. Well, there is a point uv somewhere in that region, and we could think about that as being a point xy. And if I were to write the equation of this vertical blue line, that would be x equals u, and my horizontal line, that would be y equals v. So you can see we're just using u and v instead of x and y. So applying that parametrization, those outputs, the range of this vector r, are defining this surface in space. And so you can see this is a position vector mapping from the origin to that point uv. So that point uv in the region, in the plane, the xy plane, if you will, maps up to this point on the surface. And instead of x equal u being a constant line, if we imagine that line down here, it's mapping straight up and creating a curve on that surface. The same with y equals v. Again, it's mapping directly up here and creating that curve again on my surface S. And before we begin talking about our goal for this unit or section being surface area, we need to really visualize what the parameterizations look like. So let's do some examples. Here, we're going to identify and sketch the surface with this vector equation. So we're given this vector equation, r of uv. And I have an x, a y, and a z component. So we should be able to see that I have, here I can write x equals 2 cosine u, y is equal to v, and z equals 2 sine u. So we're breaking it apart into its component pieces, and we're looking at these as x, y, and z independently. Now, there's not really one specific way I can tell you to do this, but you'll be lucky if you can see a pattern or a relationship. So let's think about what I see here with my x and z. What do these represent? X equaling 2 cosine u and z equaling 2 sine u. I pause to let you think, but that's representing a circle of radius 2 in the xz plane. So let's think about sketching this. I'll do the best I can. We've got our x, y, z, we're coming in all of these different directions. We have a circle of radius 2 in the xz plane. It looks roughly like that. So what does y equals v mean? Well, thinking about v being in terms of y, it's essentially just saying, hey, we're extending this out around the y-axis, almost as though we're extruding it, if you will. So visualizing this, I'm going to draw my circle again here. Look at our circle. I'm going to go ahead and extrude it. So really, this is parametrizing a cylinder of radius 2 around that y-axis. So some questions that we could think about here. If we created a restriction on V, I said V has to be between some specific values. What would that do to this cylinder, which currently is extending, infinitely in either direction along the y-axis? So if I restrict V, then I would be restricting the length of this cylinder. So say if I restricted my V's to be between 1 and 3, we might only be looking at a shorter cylinder in here. All right, so there's my kind of cylindrical shape if I have restricted it. Also, something for us to consider, what if I restricted U? What would that give me? So maybe I said that U is from 0 to pi over 2. How much of that cylinder would I be viewing? Well, we might only end up with a quarter of that cylinder, which you can kind of see. I've kind of sketched that over here on top. So if we did that, we could restrict the curvature portion of the cylinder. Now, you don't have to be able to graph these. I just want you to think about what happens when we create restrictions on that U and V. What does that do to this parametrized vector? And so again, restricting V could restrict the length of this cylinder. Restricting U is going to kind of restrict the curve, the arc that we're seeing show up part of the cylinder. Let's look at another example. Here, we're given our parametrized, and I just wrote it using component form instead of the IJK form. But maybe we have that my X component or my F component is U squared, my G component is U cosine V, and then H of UV is U sine V. Thinking about what these each represent, what is the shape of this surface? What are we seeing right here with my Y and Z values? What do I see right here with my X value? So looking at this, I'm seeing pieces of a circle. What is the radius of this circle? The circle has a varying radius of U, right? So this is a circle in the YZ plane of a varying radius U. So we have a circle of radius U, and then we have something here that is parabolic. Hopefully you're recognizing that this is a parabola. Parabola and a circle, when they come together, thinking about those quadric surfaces we talked about at the onset of the semester, it's an elliptical or circular paraboloid. So again, this is mostly intuition that I'm using here, but we want to kind of be able to visualize this. So understanding that this is not an exact science that I can just say, hey, you're going to do it the same way every time. And if we think about, kind of visualizing this here, I'm going to do my best job to draw this on the cuff. But we have a circle in the YZ plane. So my circles are going to be extruding out along this y-axis. So eventually I'll have some circle of larger radius out here. And then we have what is occurring here is we've got a parabolic shape traveling along that x-axis. So my curve, this is not the most beautiful, but I think you get the idea. We have this elliptic paraboloid. And I say elliptic, it's a circle in this case because those coefficients are the same. Okay, so while we're having this discussion, I want to kind of reverse our thought process. In this example, we are given a surface and we want to determine some sort of parametric representation. So I have z is equal to x squared plus 2y squared. Now, this isn't, there's not one single way you can do this. There are multiple parameterizations. So we're just going to come up with one possible idea. Now, one thing that's nice about this is that z is written explicitly in terms of x and y. So thinking about this vector represented the way our book defined it, being a function of u and v, we have x is going to be the function of u and v. Y here can be a function g in terms of u and v, and then h, that can be my z component in terms of u and v. So a possible idea is I'll say, well, I'm going to let x be u and y be v, or rather my f is equal to u and my g is equal to v. So then what would my h component be in terms of u and v? H, or z, would then be u squared plus 2v squared. So we could write r in component form as u squared plus 2v squared. Or if we wanted to make it look more like our textbook, we would say r of uv is u times I plus v times j plus u squared plus 2v squared times k. So as I've said, this is not, a unique vector. This is just one possible vector representation for that function. So we took the function, the surface, and we parametrized it into this vector form. Let's do one more example. Here, we're asked to find the parametric vector representation of z equals 2 times the square root of x squared plus y squared for z values between 0 and 1. So the first thing we want to ask ourselves is, what kind of surface is this? And what we have here is the top half of a cone from 0 to z equals 1. So we have two options for how we could represent this. The first option might be to say, well, let's let x be u and y be v, and then z would, of course, be written the square root, 2 times the square root of u squared plus v squared. It's pretty easy for us to do that again because z is written explicitly in terms of x and y. So representing r of uv in component form, it might look like this. But we have a second option. So this was A. As I again said, that last one, that was not a unique representation. So if we think about cylindrical coordinates, and the reason I think about cylindrical coordinates is because I see a circle in here. So cylindrical is just our extrusion of polar coordinates. It's taking r, theta, and then adding that z component to it. So another way we could do it with cylindricals, I could say, well, x is going to be r cosine theta, and y would also be r sine theta. And then, of course, z, well, what is the square root of x squared plus y squared equal to in polar or cylindrical coordinates? That would be 2 times r. So here we could write r, instead of using u and v, we can always use different variables. So we'll say r and theta And parameterizing that in cylindrical form, we would have r cosine theta, r sine theta, and 2r. Or we could write it this way, just using the notation from our text. And of course, if we wanted to think about that domain and range, well, what would my r values need to be between? So z goes between 0 and 1. Theta obviously goes between 0 and 2 pi, forming that full circle, so that's easy for us to think about. But if z is 1, what would r be? If z is 0, what would r be? So in this case, we would say that r is 0 to 1/2, and of course, theta is in the set from 0 to 2 pi. I know I said that was the last one, but let's just do one more. So we have one more, x squared plus y minus 3 quantity squared equals 9 for z between 0 and 5. So what is this type of equation? What surface does this represent? This is a cylinder. So cylindrical parametrization makes sense. This shape here is a cylinder. So how could I define that using cylindrical parametrization? I will say again that x equals r cosine theta, because that's how we define x in polar. Y equals r sine theta. And then how would we refer to z? Well, we would just say that z equals z. So what we notice here is I have r, theta, and z in my parameterization, and I can't have 3 variables. I want 2 variables, i.e. we have r of u and v, right? So we want 2 variables. So I've got to think about a way to maybe eliminate one of these variables. Well, if I take my equation, say I started multiplying this out, I would have x squared plus y squared minus 6y plus 9 equals 9, or x squared plus y squared minus 6y equals 0. X squared plus y squared is r squared minus 6. Y is r times sine of theta. So isolating that, that would be r squared equals 6 times r sine theta. And dividing by an r on both sides, we determine that r is 6 sine theta. So the way I had originally parametrized this, I can now rewrite that. That's x equals 6 sine theta cosine theta. Y equals 6 sine theta sine theta. And z equals z. So what you notice here is I have my, I only have 2 variables in my parameterization. Up here I had 3 variables, which made it harder for us to think about. So let's write our solution. Here we have r of theta z. Simplifying 6 sine theta cosine theta, I recognize that's the same as 3 times 2 sine theta cosine theta, or 3, that's my sine double angle. So I have 3 sine 2 theta I plus 6 sine theta squared j plus z k. And in this situation, my theta is again going to fall between 0 and 2 pi. And what will my z values be between? Well, that was given. Z is between 0 and 5. So I don't have to do a conversion for this one. So in this video, we talked both about visualizing what these parameterized surfaces look like, and then taking a surface and writing it as a parameterized vector of two variables. As always, email me if you have any comments, questions, or concerns.